Greetings to all, and a very warm welcome to all of you who are present here. This is Mohammad Junaid from Data Science stream studying in IIR. So today I am here to give a presentation on a non-iterative approximate solution method for volume conductor problem based on the finite difference method. So let's get started with the PPT. So our topic name is a non-iterative approximate solution method for volume conductor problem based on the finite difference method. So here a non-iterative is nothing but without repetition. Okay, iterative is nothing but with repetition. Okay, here non-iterative is nothing but the without repetition, an approximate solution method for volume conductor problem based on the finite difference method. So let's get into the introduction part. Yeah, non-iterative method result in the series solution and also make a use of fixed point principle. So normally non-iterative method, it results in the series solution, and it also make use of fixed point principle. Okay, now by means of integration by parts and use of certain integral identities, it is shown that the initial conditions that appear in the non-iterative methods presented can be eliminated. Okay, so we all know what is the integration. We have studied in the 12th standard about it. So normally these non-iterative methods are done by the integration by parts and with the use of certain integral identities. Okay, we have learned some integral identities in the 12th standard. So using that, we can do the non-iterative methods. Okay, so by means of integration by parts. Integration by parts is nothing but it is a subtopic in the integration concept. Okay, so by means of integration by parts and use of certain integral identities, it is shown that the initial conditions that appear in the non-iterative methods presented can be eliminated, and the resulting non-iterative technique is identical to the variational non-iteration method, which is derived without making any use at all of Lagrange multipliers and constrained variations. Yeah. It is also shown that the formulation presented here can be applied to the initial value problems in ordinary differential, Volterra's integral, and integral differential, pantograph, and nonlinear and linear algebraic equations. So here you can see that in the previous slide, we have seen integration by parts and integral identities. Along with that, ordinary differential, Volterra's integral, and integral differential. So these are the methods which are used in the non-iterative methods. Okay, so this point is nothing but it is also shown that the formulation presented here can be applied to initial value problems. So this ordinary differential and Volterra's integral and integral differential, these are the methods which are, it means applied for the basic problems. It means basic applied for the basic non-iterative methods. Okay, yeah, let's move to the another slide. Now here integral differential with a pantograph and non-linear and linear algebraic equations. So along with that integral methods, here pantograph and non-linear and linear algebraic equations. So these also are used in the non-iterative methods. So now a technique for improving, accelerating the convergence of the non-iterative methods presented here is also presented and results in a Lipskitz constant. Okay, so a technique for improving or accelerating the convergence of non-iterative methods presented here also results in the Lipskitz constants. It means nothing but, see here, the pantograph, nonlinear, linear algebraic, as well as the Volterra's integral, integral differential, and integration by parts, integral identities results in the Lipskitz constant. Okay, see, that is particularly these methods used for the non-iterative, but also when we apply that, it gives a Lipskitz constant. Okay, so that may be varied as the non-iteration progresses. Now we'll move to the next slide. It is also argued that the non-iterative methods may not competitive with iterative ones. So this non the methods we are applying for the non-iterative methods, that is completely different with the iterative ones. I have already said you that the non-iterative methods are nothing but which keeps on repetition, and the iterative is nothing but which does not repeat. Okay, so the methods I have you say, I said you before, integration by parts, integral identities, and some pantograph and non-linear, linear algebraic, and Volterra's integral and integral differential. So these methods are not used for the iterative ones. So the methods for the non-iterative and the iterative ones are completely different because of possible cancellation errors. Here, this point says that if we apply non-iterative methods to the iterative ones, then the cancellation occurs. So the methods for the non-iterative and the iterative are completely different. So if we implement it numerically, then the cancellation errors will be there. So what we'll do that while applying non-iterative ones, will not apply it for the iterative ones. Okay. Yeah. Now explanation part. See, this is a sketch of 10 by 10 grid which gives a discretization of a volume conductor. So this is a volume conductor, okay, which gives a discretization of a volume conductor. We can say this is a 10 by 10 grid which gives a discretization. See, assume it in a 3D image. Here you can see the z-axis, and here this is the y-axis, this is the y, and then here the z-axis, sorry, x-axis. This is the z-axis, y-axis, and then x-axis. So this is a 10 by 10 grid which gives a discretization of a volume conductor. Okay, now a method was introduced to approximate the solution of the large sets of simultaneous equation that results from the application of finite difference method to volume conductor problems. Here this point says that a method was introduced to approximate the solution of large set of simultaneous equation that result from the application of finite difference method to volume conductor based problems. Okay, it is based on omitting small mesh connections that arise from the star mesh transforms. It means the finite difference method to volume conductor problems, these are based upon the small mesh connection which arise from the star mesh transforms. Okay, yeah. In the finite difference network, the method has the potential to solve very large. See here, n is greater than 10 SUP5 sets of equation. So the method has potential to solve very large set of equations. See, this equation is nothing, says that this method has the potential. It means the finite difference network. Okay, this method has a potential. It means it has some ability to solve large set of equations. Okay, now large set of equations, preliminary results are presented. Now the below image shows the star mesh transform application and formulas. So now let's see the star mesh diagram. Yeah, here it is a star mesh with n components. Okay, see, these are the n components over here. Let me show you the description of it. Yeah, in the above star mesh transform applications and formula, the heavy dot, see over here, the heavy dot at center, see, these are the heavy dots. Here in the first image it is here, here, and here. Okay, these are the heavy dots. These all are the heavy dots. The heavy dot indicates the center node of a star. See, these heavy dots indicate a center node of a star. Yeah, you can see over here, this is the heavy dot. These indicate the center node of a star as sketched in the upper part of the boxes 1, 2, and 3. Yeah, here it is. Okay, this is known as the heavy dots. These heavy knots, this heavy dot indicates the star node. Okay, this. Now the star is transformed into a mesh lower parts of the boxes. Here it is. Now see, this is a star. Now here it has been converted to the mesh. Okay, as you can see in the description, the star is transformed into a mesh lower boxes. Means here, see, first it was the like this is the star node, and then it has been converted to the transformed into the mesh one. See over here, and this has been transformed like this, and this is transformed like this. Okay, yeah. C denotes a conductance per unit of volume. Here this you can see over here, C1, C2, C1, C2. This C indicates the conductance. Okay, the two per unit of the volume between a point of a star and its center node. As I have said you, this is the point. Okay, and this is the center node. This is a heavy dot. This is a center node. So this connection is known as the conductance. Here C denotes the conductance. Okay. Yeah. Now C denotes the conductance per unit volume. Okay. Between points I and J in a mesh. Here. Now here. This C denotes the conductance per unit volume. And this C denotes the conductance per unit volume. Here. Here, this C denotes the conductance per unit volume. Between points I and J in a mesh. See, this is the star one and this is the mesh diagram. So this is the I point, this is the J point, this is the C, which is nothing but the conductance between I and the J. Okay, yeah, I hope it's clear for you. Now, the formula gives the relationship between C and C, comma, comma, dot, dot, C for a general star mesh transform, assuming a star with n components. So now here it's a formula. See, Cij is equals to CICJ divided by NCT. Okay, so here this is the formula for the star mesh transformation. So this is the star diagram, this is the mesh diagram. Now the star has been transformed to the mesh one. So the relation of these two, star and the mesh transformation, the formula is given with the n components. Okay, yeah, now let's move to the another slide. Yeah. A control volume based finite difference method, finite difference method. The method is based on the widely used CVFDM solution method of heat conduction and fluid flow problems. Okay, the method normally, the finite difference method normally used for the SVFDM solution, which is of heat conduction and fluid flow problems. So the finite difference method is used for the CVFDM solution method of heat conduction and also for the fluid flow problems. Okay. Now, when solving fluid flow problems, okay, when we are solving fluid flow problems with the finite difference method, with SCVFDM, the staggered grid is often used since it gives more stable solutions and helps to avoid numerical difficulties regarding the first derivatives in pressure and velocity. Due to the close connection between the equilibrium equations and the momentum equations, the staggered grid is also introduced in the new method, and it turns out to give a rather elegant formulation. Yeah. When non-constant material properties are involved, okay, it means when we are solving, when the non-constant material properties are involved, then once the mesh has been established, the basic fluxes and equations are discretized. Okay, once the mesh, it means once the star to mesh transformation has been done, then basic fluxes and equations are discretized. This is done in detail in order to establish a concise numerical foundation. The formulation of prescribed stresses is explained in detail since it turns out to be a rather complex. The resulting linear algebraic equations are solved iteratively by Line, Gauss, Seidel. The relative nature of the displacement fields and especially what that means with regard to boundary conditions is also discussed. Finally, the numerical model is validated and discussed. Together suggestions for future work. Solving problems in the field of solid mechanics, such as the generalized Navier equations, normally involves the finite element method, which is nothing but FEM. However, some of the first methods for solving these problems actually were finite difference method, which is nothing but FDM. Indeed, FDMs in relatively rudimentary forms were in use for hand calculations even before the advent of computers. But from the mid of 1960s, the FEM has been the dominant numerical method in the field. So FEM is nothing but the finite element method. So from mid 1960s, the FEM has been dominant. Okay. A result of this has been a decreased interest in the FDM applied, so solid mechanics. And this has had a consequence, a very slowly development of the FDM related to elastic plastic problem. However, some methods have been developed and these are naturally divided into three groups. And those three groups are beam, plate, shell, and three-dimensional problems solved by the classical FDM, finite difference method, applying Taylor series and direct solution algorithms. Bates and Wilson, Griffin and Varga and Fenner. So this was the first method. Second method is finite difference energy method, which is nothing but the FDEM. This method is based on a variational formulation as well as most finite element methods. Now, third method is finite difference methods using iterative methods such as SOR and splitting, which is familiar to ADI schemes Heller, Varga, Pater, Conte, and James, Yanenko, Konovalvo, and Samaski. So three methods. These were the three methods have been developed and for the FDM related to solve elastic and plastic problems. Okay, thank you, and I hope that you understood the concept very clearly.